Welcome back, Eduvos software engineering students. I know exams are looming right around the corner, so consider this explainer your absolute masterclass review of Chapter 13. Today we're zeroing in entirely on security testing and assurance. We're going to unpack the trickiest concepts from Section 13.5 and the chapter's key points, and we'll translate them into a structure that'll help you completely lock down this material for test day. Let's get into it.
Here is our roadmap for today. We have 5 specific sections to tackle. First, an introduction to security testing. Second, the buffer overflow vulnerability. Third, 4 security assessment methods. Fourth, a Chapter 13 master recap. And finally, a comprehensive exam summary.
All right, let's jump straight into Section 1, Introduction to Security Testing.
Now, if you've been finding this chapter tough, honestly, you are in good company. Security testing is widely considered by industry professionals to be the absolute hardest phase of software engineering. But why is that? Well, think about standard functional testing. In normal testing, you just have to prove that a program does exactly what it was designed to do. But with security testing, you are essentially trying to prove a negative. You have to confidently declare, this program shall not be hacked, and that is incredibly hard. You aren't just looking for accidental bugs, you are defending your system against intelligent, highly creative human adversaries. And these attackers? They have endless time, deep motivation, and massive resources to just keep poking at your system until they find one tiny weakness.
To really understand why this validation is so difficult, let's move right into Section 2, the buffer overflow vulnerability.
Let's look at this at the programming language level. Some languages, like Java, come with built-in safety nets, specifically something called automatic array-bound checking. Basically, if you try to stuff too much data into a specific chunk of memory, the program immediately catches the error and shuts it down. It knows its boundaries. But older, heavily used languages like C and C++, they do not have this automatic checking by default. So, if a software engineer forgets to manually write the code to check exactly how much data is coming in, boom, you've just created a massive security loophole.
So how do attackers actually exploit this missing check? Through a buffer overflow. This is a classic attack triggered when a malicious user inputs massive, unexpectedly long strings of data into a field. Because the language, say C++, isn't checking where the boundary is, that massive string literally overflows its allocated memory buffer. It spills right over and overwrites the program's stack. Attackers then use this overwritten space to run their own malicious code right inside your system. So what's the ultimate defense mechanism here? Checking input formats. You must never, ever trust user input. Always strictly define and validate the format of the data your program will accept.
This brings us perfectly to Section 3, 4 security assessment methods, because obviously we need to find these vulnerabilities before the attackers do.
Okay, grab your pens because this is a huge exam focus point. You need to be able to list and clearly explain these 4 types of security assessment methods: experience-based testing, penetration testing, tool-based analysis, and formal verification. Let's break them down one by one.
First up is experience-based testing. Just like it sounds, this relies entirely on historical knowledge. The validation team manually analyzes the system against known types of attacks. They use massive, detailed checklists of known flaws. For example, they might check to make sure the system isn't vulnerable to SQL poisoning by manually typing SQL commands directly into web forms just to see what happens. It's very manual, and it relies heavily on the team's past experience.
Second, we have penetration testing. Now, while experience-based testing looks for the flaws we already know about, penetration testing is all about finding the ones we don't. For this, you bring in ethical hackers who sit completely outside your development team. Their one and only objective: actively breach the system's defenses. By simulating a real, active attack, they use their creativity to discover brand new ways to compromise your security, things the original developers probably never even considered.
Third is tool-based analysis. Instead of testing the running software, this method uses automated static analyzers to scan the raw source code itself. You're using specialized software tools to rapidly chew through millions of lines of code, looking for anomalies, missing bounds checks, or just generally sloppy programming practices that could be a weakness. Automation is absolutely essential here, because let's face it, humans just can't catch every tiny programming error efficiently.
And finally, the 4th method, formal verification. This is the heavy hitter, the most rigorous approach of them all. It involves mathematically proving that the code exactly matches the precise security specifications of the system. It is incredibly effective at guaranteeing a program's behavior. But from a realistic engineering perspective, there's a massive trade-off. It is extremely complex, incredibly time-consuming, and highly expensive. So while it provides the absolute highest level of assurance, it's actually rarely used in daily practice, being reserved mostly for a highly critical life-or-death systems.
Moving right along to Section 4, the Chapter 13 Master Recap. Let's do a rapid-fire synthesis of the core principles you absolutely need to lock in.
First and foremost, you have to know the CIA triad. This is literally the foundation of security engineering. Security isn't just one broad concept, it's specifically about resisting malicious attacks on 3 distinct fronts: confidentiality, keeping your data secret; integrity, ensuring your data hasn't been maliciously altered; and availability, making sure the system actually stays up and running when legitimate users need it. Every single security requirement will tie back to this triad.
Next up, let's talk about risk. Security risk management is, at the end of the day, a business decision. As impartial engineers, we have to accept that you simply cannot protect against everything. It's impossible. You are constantly balancing the financial cost of a potential attack against the financial cost of implementing the protection. The security requirements you gather will define exactly what techniques protect your assets, but that choice is always driven by this cost-benefit risk analysis.
Speaking of techniques, our next key principle is defense in depth. Basically, don't put all your eggs in one basket. This means employing several different security techniques across multiple layers of your system. A single failure should never result in a total compromise. Architecturally, this requires tough choices. Do you centralize your key assets and build one massive digital fortress, or do you distribute them so that if one specific area gets breached, the total loss is minimized? Defense in depth ensures that an attacker has to fight through the platform level, the application level, and the record level just to get what they want.
All right, we've made it to Section 5, the Comprehensive Exam Summary. Consider this your ultimate, definitive cheat sheet.
If you want those top marks, these are the exact facts, the correct definitions, and the specific South African English spellings you need to have memorized. Let's run through it. Remember why testing is hard? You're proving a negative. Remember your classic vulnerability, the buffer overflow, where massive strings overwrite the program stack. And remember those 4 assessment methods: experience-based testing using manual checklists, penetration testing using ethical hackers, tool-based analysis using automated static analyzers, and formal verification using mathematical proofs. Honestly, take a screenshot of this right now. It is absolute gold for your revision.
And just like that, we've reached the end of our Chapter 13 explainer. You've got the tools, you've got the terminology. So I leave you with this final thought. Are you ready for Chapter 14, Resilience Engineering? To make sure you are, I highly encourage you to tackle those end-of-chapter exercises in your textbook. Because once you understand how to defend a system from an attack, the very next question is, what on earth do we do when an attack actually succeeds? Keep reviewing those notes, good luck with the prep, and we'll see you in the next one.